Let me start by thanking the organizers for putting together this very nice conference and also for inviting me. This is my first time across the pond, as they say, so I'm very happy to be here. So I'll be talking about some work which has been going on for a couple of years at this point, but the main focus of the talk will be related to some work we put out in February of this year with Nikolai Gromov and Nicolo Primi, who's a PhD student at King's. But I'll also be mentioning some earlier work which was done in collaboration with Fedor, Levkovich, Masliuk, and Dmitro Volin. So let me give you like the one-liner version of what this talk is going to be about. So I'm going to show you a new technique in quantum integrable systems and try to convince you that this technique is essentially shaping up to be possibly the most powerful method for computing correlation functions in these models. Okay, so to get into the motivation of what I'm talking about, so ultimately what we're trying to do here is solve certain four-dimensional quantum field theories. And we've seen the words quantum spectral curve very briefly mentioned or alluded to in a couple of the previous talks so far. So if you're unfamiliar with this, let me just give you a very little brief overview. So ultimately, quantum spectral curve gives you the exact solution of planar n equals 4 super Yang-Mills. On a practical level, what it is a collection of functions which are called Q functions, which satisfy various functional relations between themselves and are subject to certain analytic requirements. So in the case at hand, these Q functions have branch points, the location of which is related to the Doof coupling of n equals 4 super Yang-Mills. And if you look at some particular state, some particular single trace local operator in n equals 4, then the quantum numbers of this state are encoded in the large U asymptotics of these Q functions. So these quantum spectral curve equations have been studied and solved and analyzed in various different regimes. For example, it's been used to compute scaling dimensions perturbatively to very, very high order. It's been solved numerically at finite coupling. And you can actually see that the results you get interpolate smoothly between n equals 4 at weak coupling and string theory at strong coupling. So the spectral problem, with all this in mind, is essentially considered solved. But this isn't the end of the story. It's, of course, n equals 4 super Yang-Mills is a conformal field theory. So to really say you've solved it, it's not enough to just know scaling dimensions of local operators. You also need to know 3-point structure constants. And the question then you can ask is, what can quantum spectral curve tell you about such objects? So from the very early days, it was kind of imagined or hoped that the Q functions from quantum spectral curve would provide the building blocks of the exact wave functions of the theory, and hence should know about correlation functions. And this was actually very recently, by recently I mean a couple of weeks ago, 6 or 7 weeks ago, shown to be true in a work by Benjamin Basso, Alessandro Gorgodis, and Arthur Suero, by combining essentially ingredients from quantum spectral curve and the hexagon program, and showing that you can actually write correlation functions using quantum spectral curve ingredients. On the other hand, in practice, these results are not particularly easy to use because these results are expressed as some infinite sum of an infinite number of integrals of the Q functions, which are actually not very easy to use. However, there are actually regimes where you don't need to deal with an infinite number of integrals, but actually just a finite number of integrals of Q functions. And we know already that the spectral problem has such a simple solution when expressed in terms of Q functions, that the same should actually be true for correlation functions, hopefully, and hence there's probably some hidden structure which is waiting to be discovered. So there are two such regimes which have been studied where the structure of correlation functions simplify using Q functions, which were studied by 2 different groups. The first group being Andrea Kavli, Kolia, and Fedor. The second group being Shota Komatsu and Simon Giombi. And essentially 2 different regimes were studied. So the first regime is looking at cusped Wilson loops in n equals 4 in the so-called ladders limit, where only a certain number of Feynman diagrams survive. And the second group looking at near BPS Wilson loops. And both of these groups show that you can actually express certain correlation functions using Q functions with very, very simple structure. And the key object which you need to actually write down the correlation function is an object which we call a bracket. And what the bracket is really just an integral operator, which takes some function, integrates it along some contour, weighted with some measure mu. And in these setups, the key property of this bracket is that Q functions corresponding to two different states, say psi A and psi B, are orthogonal. Okay, so you can essentially view this as being a scalar product on the space of Q functions. So in both of these setups, the bracket is actually quite different, but still very simple. So for example, here, the measure is just a simple 1 over 2 pi IU, and the contour is essentially a vertical line in the complex plane. Whereas here, the measure involves the Zukowski variable x, which satisfies x plus 1 over x equals u over g, where g is related to the coupling constant. And the contour is just a circle which goes around the shortcut of the Zukowski variable. And in both of these setups, you can actually compute the same object and show that when expressed in terms of the bracket, it takes essentially the exact same form in both regimes. All you have to do is take the bracket of the Q function and plug in a little extra parameter u and integrate. Okay, so this bracket is clearly a very important object and powerful object, which we would like to understand a little bit better. So what we've kind of learned in the past couple of years is that this bracket is actually a natural object in what we call functional separation of variables. So what is more generally separation of variables? Well, separation of variables dates back to the works of Scalar in the 80s, who essentially said you should try to identify a certain coordinate system called SOV basis in the integral model, where the wave functions of the theory factorize into very simple factors. And these simple factors are usually related to the Q functions of the model. And it's been known for a very, very long time that this procedure is an extremely powerful method for rank 1 models, which essentially means SL2 or SU2 models. And many, many nice things have been computed. For example, one-point functions in the Stein-Gordon model, certain hexagon form factors in a paper by Yunfeng Zhang, Shota Komatsu, Ivan Kostov, and Dedina. Boundary overlaps, as we heard about this morning, for example, in a paper by Joao and Shota, but also a paper of Thomas Gambor and Balázs Poczkaj. Matrix elements were computed in Toda models by Fedor Smirnov, and also the computation of Basso-Dixon correlators by Sergei Derkachov, Volodya Kazakov, and Enrico Olavucci, and many, many others, which I just won't mention here. So this is obviously a very powerful technique, but somehow it was only recently, in the past 6 years or so, extended to the higher rank case. So for example, SL3. And many authors have actually been working on this. Andrei Kavli, Kolya, Fedor, Grigory Sizov, Lyashik, Slavnov, Maye, Nicoli, Vignoli, myself and Dima Volin, and Sergei Derkachov and Enrico Olavucci. And the lesson which we've learned from looking at this higher rank separation of variables is that the old operator approach, largely based by Stein, is essentially insufficient and should be supplemented with a functional separation of variables. So the goal of this talk will be to describe the systematic study of correlation functions in integrable spin chains using this functional approach to separation of variables. All right, so in case you decouple, let me just tell you the punchline right now. So in the paper we put out in February, we were studying SLN spin chains, or SUN if you want, so finite or infinite dimensional representations. But for this talk, I'm just going to talk about SU2. So we've identified a very special set of operators on the spin chain, which we call principal operators. But these principal operators, I, carry 3 indices, so R, B, and beta. So R runs from 0 to n, B runs from 1 to n minus 1, and beta runs from 1 to L, where L is the length of the spin chain. So we have L times n minus 1 times L n plus 1 operators for SLN. So why do we care about these operators? Well, 2 reasons. First of all, they generate all possible observables of the spin chain. Okay, so if you know everything about these operators, in principle, you know everything. All right, secondly, they play especially nicely with separation of variables. Okay, and what this does for you is it allows you to compute all possible form factors, so matrix elements of these operators as very simple determinants of Q functions. So to give you an example, this is an example for an SL3 or SU3 spin chain of length 1. So we know that the scalar product of 2 states is given by this determinant of bracket, which is an integral, of certain Q functions. And now we take what I would consider to be the simplest principal operator, I1, 1, 1, and insert it. And its matrix elements are very simply related to the determinant giving the scalar product. All you have to do is insert this simple factor of u in the first column, which is very similar to what we saw in the case of the Cauchy-Wilson loops. Okay, so yeah, so the goal here is going to be to describe to you how to systematically compute these objects. And at the end, I'll explain quite concretely why you, the audience, should care about computing these objects and related to things we've seen already in the talk so far and the talks to come. All right, so that's sort of what we're doing. So functional separation of variables. So what is this? So what functional separation of variables means is we want to try and separate variables of the integrable system directly at the level of the functional equations which govern the spectrum of this model. So for example, in an SU2 spin chain, the spectrum is governed by what's called Baxter Tq equation. And you can imagine that the Baxter Tq equation is essentially a quantum spectral curve equation for an SU2 Heisenberg spin chain. All right, so this is what the Tq equation looks like. L here is the length of the spin chain again. Now, what are the ingredients? Well, I have Q functions, which determine the state, and I have this tau, which is an eigenvalue of what we call transfer matrix, which is essentially generating function of all the conserved charges of the model. All right, so the main idea which leads to functional separation of variables is the notion of orthogonality. So we take two distinct states, and we say, well, they should be orthogonal. Okay. However, the states are completely fixed by the Q functions, which solve the Baxter Tq equation. So if states are completely fixed by Q functions, how do we reformulate orthogonality directly at the level of the Tq equation and the Q functions? All right, so to actually put this into practice, I don't actually want to work with this really nice Tq equation here. I actually want to deform things a little bit to remove some degeneracies and so on, but this is just technicality. You can get rid of all this at the end if you want. So actually what I'm going to be working with is a twisted inhomogeneous SU2 spin chain. So as I said, for technical reasons, it's actually better to deform the thing a bit. So I want to deform by introducing these parameters inhomogeneities, theta 1 up to theta L. And I want to package all of these into a function called Q theta, which is just some polynomial whose zeros are the inhomogeneities. And then I want to introduce some twist parameters, lambda 1 and lambda 2. And it's extremely convenient and in fact crucial to package these into characters of GL2 group. So I have chi1, which is lambda 1 plus lambda 2, and chi2, which is just a product of lambda 1 times lambda 2. And then the transfer matrix for the twisted model has this structure. So its leading term is just the identity matrix times u to the L times the first character, plus some terms which depend on the state. So these are the eigenvalues of the integrals of motion. And then the Baxter Tq equation for the twisted inhomogeneous spin chain takes this form. So I now have this Q theta factor, which is now shifted, and Q theta factor, which is shifted here, but also the appearance of the characters chi2 and also a chi1, which sits inside of this transfer matrix. Okay. Okay. So the key sort of step in producing this functional version of separation of variables involves recasting the Baxter equation as a finite difference operator. So I want to introduce this finite difference operator O, which has these Q theta terms, and also this D. So this D is a finite difference operator which shifts the spectral parameter or the argument of whatever function it acts on, right? So D plus or minus 1 acts on some function f just by shifting the argument by plus or minus I over 2. Okay? So in this sense, you can see that the Baxter Tq equation is just equivalent to the statement that this finite difference operator kills the Q function. Okay? So now we start looking at brackets, and I already told you that brackets were essentially the key object within the functional separation of variables approach. So I introduce a bracket, actually a family of brackets, bracket alpha, where alpha runs from 1 to L, which is the length of the spin chain, which takes some function, integrates it with some measure, and this measure looks a bit complicated, but I'll talk about a little bit more in a moment, and I integrate over a very large circle. So this measure has poles related to the inhomogeneities plus or minus I over 2. Okay? And with this extra factor here, which is some periodic function. And the purpose of this fact is that this mu alpha is chosen or designed in such a way that it only has poles related to theta alpha. Okay? Because this factor here is going to kill all the poles related to the other inhomogeneities. And then this contour is chosen so that it goes around all the poles of all the measures. And then actually, the key point is that the Baxter operator, which gives you the Tq equation, is essentially self-adjoint with this bracket. Okay? What this means is that up to a simple factor chi2, which is related to the twist, that you can rearrange the order of two functions inside the bracket, which the Baxter operator acts on. So you see here I have f, and then I have o acting on some function g. Well, this is actually equal to the same thing, but the order of f and g reversed. So in this sense, we say that this Baxter operator is self-adjoint with this bracket. And then some trivial identities which follow from this is that, first of all, we have this, And the reason this is true is trivial, just because O or Q is the Q function, which is killed by the Baxter operator. So this is just trivially 0. Here we have this. And what this is saying is that this O kills a different Q function, Q bar, acting on the left, where Q bar is just related to the original Q function times this twist factor, which we had here. Okay, and the reason this is true is just simply because you can then swap the order by the self-adjointness condition and get that O acting on Q is equal to 0. So you have these two equalities. Okay, so now what I want to do is to consider two distinct states of the model. Let's say psi A and psi B. And then I consider the Q functions associated to these states. So to psi A, I associate QA, and to psi B, I associate QB. And then I consider the following very trivial equality. So I have the finite difference operators associated to these two states, so OA, and then I have minus OB, and I sandwich them between two Q functions associated to the state A and the state B. So this is 0, as I said, for trivial reasons. So it's 0 because, first of all, OA kills QA, but also OB kills Q bar B when acting on the left. Okay, so this is just 0. And now I take the Baxter operator and I expand. So when you plug in O into here, because you have the difference of two Baxter operators which depend on the state, only the state-dependent parts are going to survive when you take this difference. So this part here and this part here are independent of the state. The only part which depends on the state is coming from the eigenvalue of the transfer matrix. So when you plug this in and expand the transfer matrix into its integrals of motion, you get the following equality, which is true for any alpha, and you have L such alphas. So essentially what this gives you is a homogeneous linear system for the difference of the integrals of motion. But now you say to yourself, well, if these are really two different states, then there should be some integral of motion, which is some difference of integrals of motion, which is actually not 0 for two distinct states. Otherwise, this whole thing would be trivial. So in order for this to actually have a non-trivial solution, the determinant of this linear system must be 0. Okay? And what you find then is that up to a simple normalization, that the scalar product between these two states is precisely then given by the determinant of this linear system. And why is this? Well, this determinant already produces a crucial feature of the scalar product, namely that it should be 0 for two distinct states. And I've already told you that if I have two distinct states, the determinant of this linear system must be 0. All right? So then you can ask yourselves, what about the diagonal? What about the actual diagonal case when the two states are the same? And you can actually show, using some work and relating it to the operator construction of separated variables, that this determinant still produces the scalar product between the two states. Okay? And you can further show that this agrees, for example, with the scalar product coming from the SOV of the type of Sklein. Okay? So this is the scalar product, but the scalar product is only one such object you might like to compute. So next up are what are the other observables which we can compute. Okay? So let's rewind all the way back to quantum mechanics 101, where we have so-called Hellmann-Feynman theorem, which says take some conserved charge, for example, the Hamiltonian, which has eigenstates, left and right eigenstates psi, with the same eigenvalue E. And what this theorem tells you is that you can compute a non-trivial operator, which is the derivative of the Hamiltonian with respect to some parameter, and compute its matrix elements, and you find that the matrix element is given by the derivative of the eigenvalue with the same state. And using, of course, we can do all of this in the spin chain setup, but these functional separation of variables or functional orthogonality allows you to actually compute this without needing to take a derivative, really at a fixed value of p of the eigenvalues. So to see how this works, so as I said, p is some parameter of the model. So pick your favorite parameter of the model, twist, inhomogeneity, anything you like. Okay, and shift this parameter by some small amount delta p. So when you do this, all of the objects you have in the model are also going to get shifted. So the q functions will be shifted by some amount. So q will now become q plus delta q. But also the Baxter operator, which encodes the integrals of motion, will also shift. So O will now become O plus delta O. However, O plus delta O acting on q plus delta q is still 0. All right. So you can take this, you can expand to first order in the variation, send the variation to 0, and by using the orthogonality of the difference operator, what you find is this very simple relation, that when inserted inside the bracket, this derivative of the Baxter operator with respect to whatever parameter you choose still gives you 0. Okay? And now the rest is very simple. You can start again with the Baxter operator, which I remind you has this expression here. Okay? And what I want to do is separate it into two parts. The first I call y. So y encodes all of the parts which do not depend on the state. So the parts which are independent of the state are this part here. So there's q theta with my shift operator, this chi2 with q theta and my other shift operator, but also the leading term in the transfer matrix, which I remind you was given just by the first character. So this is all the state independent information. So this y precisely looks like this. And when you plug in this into here, and by using the fact that O is given by this, you can rewrite this system of equations as an inhomogeneous linear system for the derivatives of the integrals of motion with respect to whatever parameter you choose. So this is an inhomogeneous linear system, and you can just solve it using Cramer's rule from linear algebra 1. Okay? So what does Cramer's rule tell you? Well, it tells you that in your inhomogeneous linear system, on the left-hand side, you have a matrix which acts on some vector and produces some other vector. And the solution of this linear system is just given by taking the matrix of the homogeneous part and in each column replace the inhomogeneous part. Just standard Cramer's rule. So this is the solution. So the variation or the derivative of the integral of motion with respect to whatever parameter you choose is given by this. So on the bottom, I have the determinant which corresponds to the scalar product, so the homogeneous part. And on the top, I have this notation here, which means to replace column beta with this vector, which is again q bar derivative of y with respect to p times q. So to show you precisely what this means, this is the homogeneous part corresponding to the scalar product. Okay, if you just write it down for the 2 by 2 case. And then 1 goes to this, means I just replace the first column with this vector. And then 2 goes to this, means I take this and replace the second column with this vector. And by just rewriting this and using the Hellmann-Feynman theorem, what you find is that the matrix elements, or the diagonal form factor of this object, which is a quite non-trivial object, is just given by taking the scalar product determinant and replacing the corresponding column with the corresponding vector. Okay? And you might think that, like for example, if you take something like the hydrogen atom and you try to apply this technology, then when you compute the derivatives of, for example, the Hamiltonian with respect to some parameter, it's not always clear what the physical meaning of the operator you end up with is. Whereas in this setup, the operators we get are not some crazy operators we don't understand, but they're actually very physical operators. For example, if you choose this parameter p to be some inhomogeneity of the spin chain, you can construct local operators acting on a given side of the spin chain. If you do something fancy, like for example, conformal fishnet theory, which has a spin chain description, then by taking this parameter to be the coupling constant, you can compute correlation functions which correspond to Lagrangian insertions. Okay, so they're really operators we have a precise control and understanding of. But diagonal is kind of boring, let's be honest. If we really want to say we know everything about something, we want to have all possible matrix elements, all possible diagonal matrix elements. So is this the end of the story, or can we actually upgrade everything to the off-diagonal case? And in general, if you look at something like the Feynman-Hellmann theorem and you try to upgrade it to off-diagonal, you immediately fail. It just doesn't work. Furthermore, you have a single derivative of an integral of motion. You can try to upgrade to more derivatives acting on the integral of motion. This also fails. Okay? So it seems like this is the end of the road, but actually, in the spin chain setup, if you choose the parameter p very appropriately, all of this can be extended in a number of different ways. So if I choose p to be the twist eigenvalues, say lambda 1 or lambda 2, then this expression, which was true here from the previous slide, survives a number of very important upgrades. First of all, you can make it off-diagonal for free, just by replacing the q functions in the determinant with the q functions for two corresponding states. Second of all, you can put in any number of derivatives with respect to the twist eigenvalues as you like. Okay? Furthermore, and which is very cool, the two states on the left and the right-hand side do not even need to be Hamiltonian eigenstates. So for example, in the beta Ansatz approach, you have on-shell beta states, which are eigenvectors of the transfer matrix. Using this approach for free, you can replace these on-shell states with off-shell beta states. And the result will still give you some determinant of q functions. These q functions will no longer satisfy the Baxter equation because they're not on-shell, but the structure is exactly the same. But this is a sort of very special class of states which we call factorizable states. And furthermore, and very, very, very importantly, to say we've really solved the model, these operators which you get in this way generate the full algebra of observables of the model. So if you know the full matrix elements of all observables, well, you have everything. Okay, so how does this work? Well, this functional approach, which I've been sort of really pushing so far, can only tell you so much. If you want to really know what operators you're looking at, you need to build the spin chain in an operatorial way and have a look at this. So how do we build an SU2 spin chain? So we start with some lax operator, so this Lij, which depends on a spectral parameter u, and is given u times delta ij plus I times these operators e, which are related to the spin operators of SU2. So E12 is just the raising operator, E21 is the lowering operator, and so on. From here, you use the lax operator to build a monodromy matrix, where you just take copies of lax operators around the spin chain. And these operators, Tij, satisfy a very nice algebra, which is called Yangian algebra. Okay? And from then, you can take the trace of this monodromy, twisted with some matrix G, to give you the transfer matrix. And this transfer matrix generates all of the integrals of motion. So in here, I have this twist written sort of a bit vaguely. I haven't really said what it is. So this is sort of a key point I want to stress here, is that the choice of twist in this setup is really very important. Usually when you look at integrable spin chains and you want to twist it a bit, you would generally just take your twist to be diagonal, which is sufficient for regulating the spectrum, and call it a day. Okay? I don't want to do this. The natural choice would be this. However, this Yangian algebra has a certain GL2 covariance, meaning I can essentially perform some similarity transformation on the twist and replace it with any other twist I like. And for the purposes of this talk, this twist is actually the best one. So this is what we call the companion twist matrix, which has entries chi1 and chi2, 1 and 0, where chi1 and chi2 are the characters from earlier, which are just the trace of the matrix, and chi2 is the determinant of the matrix. And you can check that the eigenvalues of these two matrices are actually the same. Okay, so the trace of this is lambda1 plus lambda2. The trace of this is chi1, which is lambda1 plus lambda2. And the determinant of this is lambda1 times lambda2, which coincides with this. Okay, so I really want to stress this is not a loss of generality by choosing this twist. Because I have GL2 covariance, I can really choose any twist I like to make things simple. And I can always go back to the diagonal case and then take the untwisted limit at the end if you want. Okay, it's not a loss of generality. So when you compute the transfer matrix explicitly using this twist, so I remind you the formula which was here, so Tij, Gji, and then sum over I and j, you get the following expression. So you have T12, chi1 times T11, and chi2 times T21. So I need to stress that these T12, T11, and T21 are elements of the original monodromy matrix. So there's no twist in these guys. Okay? So why is this a particularly nice twist? Well, actually, what we discovered in actually my very first paper ever was that the separated variable basis which you construct using this twist in the type of spline is independent of the twist eigenvalues. Okay? What this means is the SOV basis is independent of twist. You can actually factorize wave functions corresponding to different Hamiltonian systems. For example, different spin chains which are related by different choices of twist. Okay, so now I can introduce our main players, which are principal operators. So as I showed you on the last page, the transfer matrix has this expansion into characters. Okay, and the transfer matrix also has an expansion into integrals of motion. So what I want to do is essentially combine these two expansions. So using this character expansion, I can define the coefficients of the characters as these operators here, P. So P0 is just T12, P1 is T11, and P2 is minus T21. Furthermore, I could do the same expansion at the level of the integrals of motion. So I could take an integral of motion, I beta, and again expand it linearly in the characters. Okay? So these operators which you get from doing this procedure, I call principal operators. So there's some abusive terminology. You can either call principal operators the P's or the I's. So the P's are just a generating function for the I's. When you expand the P's as a power series in the U, you just pick up the I's. Okay? And this notation was actually not originally intended to be Russian ruble, but actually P for principal, but also when you do principal value integration, you put a little line through the integral. So we also put a little line through the P. And furthermore, these principal operators are actually by themselves a complete algebra of observables in a sense that the remaining element of the Yangian you can generate just by doing RTT relations. So these guys by themselves generate everything. So what I'm going to show you now how to do is to compute the matrix elements, off-diagonal matrix elements of these operators. So you can either think of P itself or the components of P in the U expansion, the I's. Okay, it doesn't matter, it's the same story. So the starting point for this procedure is the scalar product. And I remind you that the scalar product is given by up to some normalization, which doesn't depend on the state, this determinant of Q functions, which is a determinant of bracket of Q functions, where the bracket is again contour, integral over some contour weighted with some measure mu. And now I want to consider the following very trivial equality. So I remind you the notation that beta arrow this means I replace column beta prime in the determinant with the corresponding vector which I have here. And this is trivially going to give me 0. Why is it going to give me 0? Because I have the Q function for state A, which is acted on by the Baxter operator for state A, and the Baxter operator kills the Q function. So I'm replacing some column in the determinant with 0 all down along the column. So this is just 0. Now I want to use, again, the fact that the Baxter operator can be expanded into a part which depends on the integrals of motion and a part which does not depend on the integrals of motion. And when you do this, you find that, because the transfer matrix had some sum over the integrals of motion, when you plug in this, you find into column beta prime that only a single integral of motion is going to survive because of the anti-symmetry of the determinant. Only the integral of motion beta prime is going to survive when you plug this thing into column beta prime. Okay? So you have this expression, but now this IA is just the eigenvalue of the integral of motion operator on the state psi a. So for free, you can just move this inside the scalar product and replace it with the operator. Okay? So what you've computed here is the matrix element of an integral of motion. So matrix element of integral of motion is kind of boring. Okay? So from this, for free, I'm going to extract all matrix elements of the principal operators. Let's see how to do this. So this is the expression we have. On the left-hand side, I expand the integrals of motion into the principal operators, which I remind you were just the coefficients in the character expansion of the integrals of motion. On the right-hand side, I replace the y, again, in terms of its explicit expression, which had difference operators. So q theta, d to the minus 2, and then I have chi1, and I have this chi2 term here. And again, you see that the right-hand side is also linear in the characters. Okay? So I have, sorry, this is a typo, this should be O0. So O0 has no character in front of it. O1 has chi1 in front of it, and O2 has chi2 in front of it. So O2 is just this thing. O1 is just minus u to the L, and what should be 0 is just q theta, and then this d to the minus 2. Then you say to yourself, okay, this is amazing because the left-hand side and the right-hand side are both linear in characters. Okay, so let's do the most naive thing we can, and let's declare that the left-hand side coefficients are equal to the right-hand side coefficients. All right, and this is a technique which we call character projection. And now there's a huge caveat, because this would be fantastic if there was absolutely no other twist independence in the game. But there's twist independence everywhere, because the Q functions contain twist, and the states also contain twist. However, you can actually show that by using the operator construction of the separated variable basis, together with the twist independence, that this equality of relating the left-hand side to the right-hand side is a totally legal and legitimate thing to do. And what you find is that the matrix elements of all of these principal operators, these i's, which appeared in the character expansion, are just given by replacing the corresponding column in the determinant with the corresponding difference operator. Okay, so for free, starting from the scalar product, you do get all this. So there's no like hardcore quantum algebra involved in this, which you might expect because it's essentially representation theory. The most complicated thing I've done is solve a linear system using Cramer's rule. Okay, so this was the story essentially for SU2, but SU2 is sort of boring. So how can you extend all of this? So the first thing you might think of is, well, okay, let's try to extend to some non-compact spin representation. So I remind you that in the SU2 case I discussed, the bracket is just given by this integral around all the poles of the measure, which is given by this. Okay, so the poles for the measure mu alpha are given by theta alpha, and then plus I over 2, and then minus I over 2. Okay, and then I encircle all of these. If you want to go to, say, non-compact spin minus s, which looks like this, so the measure gets upgraded. Okay, it's just this part here, and then it's epsilon term, which is just this ratio of gamma functions related to the choice of the spin. The only other thing you need to do is to change the contour. So instead of being essentially starting with a circle going around all the poles, you replace it with an integral over the real line. And then you can actually show that for this choice of spin, all of the poles of the measure sit in the lower half of the complex plane. You can close the contour in the lower half plane and replace this integral as a discrete sum over the corresponding residues. And when you do this, the result which I showed you for the principal operators, when expressed in terms of the bracket, is completely invariant. But this expression here does not depend in any way on the choice of representation. all information about the representation is contained inside the bracket, which is chosen essentially by the contour and the measure. Okay, so this result is completely invariant and independent of choice of representation. This is really crucial. Okay, so this was SU2, and of course you know that if you look at integrable spin chains for SU2, generally results are nice, but the moment you try to generalize to higher rank, you start having a really bad day. Okay, so what I want to stress is that the approach I've described generalizes almost for free to higher rank. You can do SUN, SLN, anything you like. So all you have to do, and I'm not exaggerating, is extend the range of indices, and then everything works for free. So the integrals of motion. So before I showed you this I beta. So now, well, these were coming from the transfer matrix, but in the higher rank case, I don't have just one transfer matrix. I have a family of transfer matrices. For example, in anti-symmetric representations of the symmetry algebra. So what was originally I beta now becomes I b beta, where b runs from 1 to n minus 1. And these dual Q functions I showed you, which were this Q bar, now we have a family of dual Q functions, which Q bar A, where A runs again from 1 to n minus 1. And what you can show that the scalar product for SUN or SLN, again, is given by a very simple determinant. Now the columns and rows of the determinant have two indices, but again, it's essentially the same idea. You have a bracket of Q functions, and now you also have this difference operator inserted here acting on the Q functions, where this D, again, shifts the argument of the function at axon just by plus or minus I over 2. And again, the bracket is, again, some very simple measure, and you have some very simple contour. So again, this result does not depend on the choice of representation. All information about the representation is contained inside the bracket. Okay? So what about principal operators and our form factors? So now for SLN, we don't just have two characters, chi1 and chi2, we have a family of characters, so chi1 up to chi-n. The transfer matrices become TA, where A runs from 1 to n minus 1. And the principal operators, which again appeared in the expansion of the transfer matrices in characters, now pick up an extra label A, because each transfer matrix admits an expansion which is linear in characters. So I have n minus 1 of these principal operators A and another index R, which corresponds to the character. And again, you can expand these principal operators into their coefficients in the U expansion. And again, in exactly the same way, you can show that the matrix elements of these operators are just given by replacing the corresponding column in the determinant, determined by the indices, with the corresponding Baxter operator, which is determined by the character. Okay, so this is everything in the Hamiltonian eigenstate basis, but this is actually not very convenient if you want to look at multiple insertions of these operators. So we know how to build the separated variable basis explicitly for any rank SLN. So we also know that for example, SL3, you don't just need one separated variable basis like you did in the case of SU2, you actually need two separated variable bases. One basis factorizes the left states, one basis factorizes the right states. And for this one, you just have a simple product of Q functions. Here you have a product of the determinant of Q functions. And what you can show is that starting from this expression, you can expand out the determinant, perform all the integrals, and rewrite it explicitly as a sum over the wave functions at the different values of the arguments which appear here. And inside here, you have the matrix element of the principal operator here. So this is in some sense a much better object to have instead of this, because with this, you can insert it as many times as you want. So this expression here is actually just a very simple rational function of the spin chain inhomogeneities, okay? And with this, as I said, you can insert compute correlation functions with any number of insertions, but only needing to know the Q functions of the two external states. Okay, and I'll comment on this a little bit now. So just to compare how all this approach works with different approaches. So traditional methods here, I mean essentially beta ansatz types approach. So first point, beta ansatz types approach always work with beta roots directly. However, beta roots are not actually a very convenient object to work with. So even if you consider just rational, highest weight, fundamental spin chain, Q functions are a much better object and can be computed much more efficiently than beta roots themselves. So for example, Dima and Christian had a paper back in 2016 where they verified this and showed how to compute the Q functions up to like length 12 or something very easily. All right, but also, if you look at models which are not highest weight, then you don't have beta roots. Okay, if you look at some principal series type representation, you still have Q functions. So being able to express observables directly at the level of Q functions is a huge advantage for these models. Okay. Beta ansatz types approach also really require having a highest weight state. Okay. On the other hand, our approach absolutely does not care about having a highest weight state. It works, for example, in conformal fishnet theory. There is no highest weight state there. Beta ansatz approaches are perfectly fine for SU2, SL2, but the moment you go to SU3 or higher rank, everything just essentially collapses and it becomes very, very difficult. In our approach, all SLN are on the same footing. Just extend the range of the indices and you're done. And multiple insertions are very difficult in the beta ansatz types approaches. Why? So you can, of course, compute the matrix element in like the beta ansatz types approach by just taking the operator you want, acting on the beta vector, moving whatever all the way through the B's, acting on the vacuum, getting some big recursion relation, and so on. All right, this is very difficult. However, in the SOV basis, this is simple, okay? Because you don't need to know anything other than the two external states. Whereas if you do this, and you insert, for example, resolution of identity between each of your operators, at every step, you need to know the Q functions or the beta roots of every single state in the theory. Okay, here you don't. You just need the Q functions of the two external states. And anything in between is just some simple rational function of inhomogeneities, which we give you a mathematical code for. All right, so spin chains are great. I think we all like them. But really, we want to talk about 4D quantum field theory. So how much of this survives? So let's talk about conformal fishnet theory first. So remarkably, or maybe not remarkably, if you believe in integrability, all of this still works. You can compute the scalar product between two states in the fishnet theory, which corresponds to a two-point function, as again, just as a simple determinant of the Q functions. The only difference here, which makes things a little bit more tricky, is that all of the Q functions now start to have poles. Okay, but this is really more of a technical difficulty. It's not really conceptual. And furthermore, because of this, these poles, it's not always clear which combinations to choose to make this expression particularly nice to evaluate. For example, some choices of Q functions would use some double poles which have to be evaluated, whereas other ones are particularly nice, and essentially if you compute the thing, poles will actually cancel out and you get a very nice thing to evaluate. Okay, but still, the original thing I mentioned about the diagonal form factors all works, as was demonstrated very nicely in this paper by Andrea Coya and Feather, where we can really compute, for example, 3-point correlation functions in fishnet theory with some Lagrangian insertion, and you get some expression like this. So again, I have this is essentially the bracket where I have some integral with some measure, which is some simple thing here, and then some vertical line, and then some factors here related to the Q functions again. Okay, and fishnet theory is great, but really we want to talk about n equals 4 super Yang-Mills. So how much of this works? Well, the key ingredient you need, which is this self-adjointness condition of the Baxter equation, still works. From quantum spectral curve, you can construct this operator O. It's again now some fourth order finite difference equation acting on Q functions, and this will work. The only thing which is different now is the choice of measure, which also starts to have cuts and so on, but it's all still there. The main difference versus the fishnets is that n equals 4 super Yang-Mills is of course dual to some nonlinear sigma model. In the fishnet theory, it's dual to a discrete chain of particles. So you have a discrete quantum mechanical system, which means all of your determinants are finite size. In this setup, you're essentially forced to deal with determinants of infinite size, and this is not necessarily clear how to work with, or at least make them tractable. However, it's expected actually at each order in perturbation theory that these determinants will actually reduce to something of finite size, because this is of course true at the leading order. Furthermore, the transfer matrix, which for me was polynomial, is no longer polynomial. So you need to ask yourselves, how do you expand it in a nice way to get a good basis of integrals of motion to go through all of this story? All right, so to summarize, I'm telling you about a new approach to correlation functions in integral systems of essentially any rank, which is based on a technique which we call functional separation of variables. And what we've done here is identify a distinguished set of operators, which we call principal operators, which generate all possible observables. And by using this framework, we can compute the Hamiltonian and the separated variable matrix elements of any of these principal operators. And we can also compute any number, correlators with any number of insertions. And most importantly, this approach extends trivially to any rank. So my first outlook, where I try to sell all of this to you, the people here in the audience. So what can this do for you? So we saw yesterday Volker's talk, Godin models or limits of Godin models and the relation to conformal blocks. So the key object here, Volker's talk, was the wave functions. So we don't have the wave function directly with this model, but we do have the scalar product. And what one could essentially try to do is read off the wave function directly from the scalar product itself. And this is actually something we try to do in the case of the XXX spin chain, and it actually works. By taking the scalar product, you make an educated guess for what the wave function should be, and then you can actually construct the separated variable basis which produces this, and then try to compute the wave function itself in the basis you want, and then compute anything else. All right, boundary overlaps, which we heard about yesterday in Charlotte's talk and also today in Shota's talk. So I've shown you that this functional separation of variables gives you the scalar product as a determinant of Q functions. So in Charlotte's talk, we saw that the boundary overlap, one of the main ingredients was the Godin matrix. Okay, so a question you can ask yourself is, how should this Godin matrix be modified to extend to finite coupling? Because the finite coupling, we don't have the beta roots. Okay. However, because we started with some determinant, it was actually shown in two separate papers, which Shota mentioned earlier, one by himself and Joao, and also a paper by Andrea, Collier, and Feather, where if you take the determinant corresponding to the scalar product, do some manipulation on the determinant, adding rows, columns, and so on, and you can actually factorize the determinant. One of the determinants you get from this factorization has precisely the property that you would expect from the boundary overlap, namely that it's 0 if the states do not have the desired parity property. Okay, but this is definitely something to explore. Next, which I believe we will hear about tomorrow in David's talk, relates to the ODE-IM correspondence. So in the ODE-IM correspondence, you have essentially some integrable system and some classical ordinary differential equation. But the key object you start with in the integral system side is really the Baxter Tq equation. And we know that we can map all of this to some very nice objects. For example, you can use this ODE-IM correspondence in the computation of scattering amplitudes, for example. But the question is, since you start with the Baxter Tq equation, can you carry out the functional separation of variables method directly on the ODE side? And will this lead to some correlation functions or scattering amplitudes in some integral quantum field theory? Next, regarding Ellie's talk, which I believe we'll hear about on Friday, regards the uplifting of all this to dynamical spin chains. So dynamical spin chains in the context of the Skleinen type separation of variables were studied. I believe there's some papers of Nicoli and collaborators where they essentially carried out the Skleinen as a procedure. However, for the case of the dynamical spin chains, which you'll need for this, like 4D n equal to 2 superconformal field theory application, you essentially have some higher rank type dynamical spin chains. However, at least in the cases which are already known, for example, dynamical XXZ type models, you still have a Baxter equation. So all of this which I've described should go through without problem. Okay? Which should then hopefully be usable to compute some correlation functions in the n equal 2 theories. So outlook number 2, where I just highlight some interesting things to consider. So the first natural one is the extension of all of this to supersymmetric SU or SL/M/N type spin chains. And most importantly, for example, the Hubbard model. Why the Hubbard model? Because it would be a very useful testing ground for n equals 4 super Yang-Mills, because they have a very similar structure. You have the Zukowski variable everywhere, you have cuts everywhere, the Q functions are quite similar as well. And the quantum spectral curve for the Hubbard model is explicitly known, at least by two different groups, Andrea Cavaglia, Ragliotto, Italiano, and Sateo, and also Simon Eckhammer, who's here, and Dima Volen. Next will be very important, which is to compare the results here with the recent hexagon proposal for correlation functions of short operators. Okay, so the idea would be to set up their proposal directly in the fishnet theory, and then see if you can compare the correlation functions you get there with the correlation functions you get in our setup of the principal operators. Next, of course, naturally, if you want to look at CFTs in various dimensions, we should look at other algebras, for example, SO2R. And the spin chain quantum spectral curve, which essentially means QQ relations and so on, has been very extensively studied recently by a few different authors. Simon is at least here, so if you're interested in that, you can speak to him. But still, there is a huge number of mysteries. So something as simple as the Baxter equation is not known in SO2R spin chains, or, for example, spin chains of, well, different algebras. Okay, well, up to some caveats. Next will be the interpretation of principal operators in the fishnet theory, and how to use these results to actually compute correlation functions directly there. And finally, we should look at open boundary conditions. So why do we care about open boundary conditions or open spin chains? Well, we've heard a lot about this, well, why we should care about this in Shota's talk, but also conformal fishnet theory has a description in terms of a closed periodic spin chain. There's another setup, which is the Cusp-Wilson line in n equals 4 super Yang-Mills in the so-called ladder's limit, which also has a dual description as a discrete open spin chain. So the question then would be that if all this essentially works for fishnets, we should try to get it to work in the case of the Wilson line, which would also lead to, hopefully, very nice results. And this is ongoing with Koya, Nicolo, and myself. All right, thank you very much.
Yeah, thank you for the talk. It's very beautiful that you have shown us how to compute the matrix elements of integrals of motion, or derivative of integrals of motion. But I think it's how do you do when you want to compute, for example, the matrix elements of spin operators,
right.
raising, or since you want to compare with the 3-point function in a DSCFT, how do you set up the correlator of 3 non-local operators?
Right. So to address the first question, right. So for the spin operators, so the starting point would essentially be here, for example. Okay. So if you know these operators in this basis, then you can extract from these operators the local spin operators. For example, using the usual inverse scattering type transform. So I claim to you that these operators generate all possible integrals of motion. So I really want to stress that the local spin operators are also included in these operators in well, generally some quite complicated way. However, if you're interested in, for example, some two-site correlation function, then you can use the usual techniques of the inverse scattering transform, rewriting the local operators in terms of the global ones, and then so on. This would all work, no problem.
And this determinant formula is also usable?
So for the case of just like matrix elements of a single spin operator, so like 1-point function, then yes, you'll have this determinant form, but you'll also have some transfer matrices dressed on the outside of the determinant. But yes, essentially the same structure is true, yes. And with regard to the question about ADA-CFT, this is of course a great question, and I probably cannot give something super precise, but if we at least restrict ourselves to the case of fishnet. So, as I said, in fishnet, this result essentially holds. So, in the fishnet theory, these states here will correspond to some local operators. Okay, so this 3-point function is essentially going to mean that you have some operator here, which in fishnet will be some differential operator, which acts, well, if you consider the 2-point function of the scalar product, then we know how to express this in terms of Feynman diagrams. So when you insert some operator here, what you're essentially doing is acting with this differential operator on the Feynman diagrams and changing it essentially at every loop order. So what this precisely corresponds to in the fishnet theory is not clear. The question would be is, can you see how these modify the Feynman diagrams, and can you see if this modification is enough to generate all possible modifications? So I'm not claiming that this will be literally a 3-point function, but at least will be the building block of a 3-point function.
Thank you.
Okay, York, so it's your turn. Could you speak up?
Yeah, thanks. Hi, very interesting. I mean, a few ingredients in the answer you presented, especially sort of these determined representation in terms of overlaps built from the Q functions, reminded me of the story of fermionic basis of Smirnov, Jimbo, Miva, and did you look into this? Is there some comments one can make on the relation to this? It looks like somehow the output has similarities, and also sort of from the background, seems that separation of variables technique has played some role for their approach. So is there some comparison that one can make already?
So the short answer is I'm not fully convinced of what the answer is. So I was at a conference 2 weeks ago where Smirnov was present and also presented some results in this fermionic basis. And again, you see that their correlation functions are again expressed as some very simple determinant type objects. So it would of course be very interesting and very important to check if there is some precise relation, but at the moment it's not completely clear to me what that is.
Okay, thanks. Sounds interesting. Yeah.
Yeah, I have a question. So, you know, there is this gauge-beta correspondence between integral models and 2-2 theory. Now, looking at all your beautiful story, it's natural to imagine that everything you do has a reformulation in terms of 2-2 theory, in terms of some properties of twisted color ring. And so I have some vague comments or thoughts on that, but how much has been done, or is it completely open? Or?
So my understanding is that most of this is completely open. So with regards to what you're describing, so well, my knowledge on this story is not completely full, but my understanding is, for example, you know that the beta equations, for example, in some integral system, map to some vacua in the n equal 2 theory.
Yes.
So I'm not aware of what the interpretation of some higher observables is, for example, in the n equal 2 theory. So here I'm looking at form factors. I haven't seen anyone describe what form factors would correspond to in the n equal 2 theory, or if there is some interpretation.
I see. So for example, you're trying to construct algebra operators, etc. It's somewhat reminiscent of, well, maybe this is not true, but for example, there's at least a natural algebra, which is the twisted chiral ring. So there might be some connections.
Yeah, absolutely.
Yes.
I think
see.
there
Okay,
probably is. Yeah.
I'm happy to discuss. Further.
Okay.
Yes.
So how easy it is it expected to be to extract a perturbative expansion analytically in the case where it exists? It sounded like for the fishnet, it was like manifestly you were doing things, but what about in n equals 4? Does that remain to be seen?
So in n equals 4, it absolutely remains to be seen. Yeah. So again, the main thing which I use is the fact that we have this Baxter operator, which we can expand into a nice basis of integrals of motion, which we just take by the usual polynomial basis. In the case of n equals 4, you can do a similar expansion, but the problem is now that the thing which corresponds to the transfer matrix is some function which has cuts all over the place, but still has some nice, like behaves, it's power like at infinity. So you should be able to start at infinity, expand, and so on. And the hope is that perturbatively only a finite number of things will contribute at each perturbative order. So it would actually be very nice to check this. No one has actually checked this, for example, even at Tulip. But I think that would be a very nice place to start. I think it can definitely be, like in practice, perturbatively, definitely it can be done. Non-perturbatively, well, I'm hopeful, but remains to be seen.
Thanks.
I have a related question to the with Masahito's comment. Can you sum over the states based on this this orthonormal basis, like a sum over beta states, and because it's something like, for instance, in index computation, you have to sum over beta roots and to get something. Is there any way to compute based on your formalism?
So it depends precisely on what you want to do. Of course, you can take, for example, like this object, and you can of course just replace the psi with some sum over beta states. But whether or not the result will have some very nice, like compact determinant form is not completely clear. And in fact, I would expect it does not. But it depends on what you want to do. I mean, of course, you can take something like this and replace beta state with sum over beta state. No problem.
So if there are no further questions, let's thank Paul again.